this. Welcome to the second session of this non-associative workshop. I want to start by thanking Ivan for putting it through. And the first lecture in this session is by Kurusch Ebrahimi-Fard from Norway on post-group theoretic perspective on the operator valued S transform in free probability. Please.
Okay. Can you hear me? Okay.
We see the slides.
Thank you. Thank you for the invitation and for giving me the opportunity to present this work from 24, which in fact is joint work with a student from Paris, Ringeard. And we wrote together two preprints, and I will sort of present what we did in the second preprint that followed the first one. The first one has been published and is more combinatorial, and this is more algebraic or group theoretic. But the topic is trying to understand what is some specific identity or factorization property of the so-called operator valued S transform in free probability. So my title, of course, contains many objects, is postgroups and operator valued S transforms in free probability. I will mainly limit myself to the algebraic group theoretical side. So I will repeat this in a second, but in my talk there won't be any probability, because for what I present, this I think is not critical. So let me maybe start with an aim of my talk. And I will sort of repeat this. But I think this is maybe then helpful to understand what I would like to present. So what is this talk about? It's somehow addressing an algebraic identity, the so-called twisted factorization property of the so-called S transform in free probability or operator valued free probability. So for this, in principle, we have to put ourselves into the context of a B-valued non-commutative probability space. So this is this triple here, where A is usually a non-commutative associative algebra. And what we are interested in are so-called formal multilinear function series, mult-B. So this infinite sequence of n linear or k plus 1 linear maps here from B into B. B is usually particular algebra, maybe a subalgebra of A, or an algebra that is sort of nice properties with respect to A. I will say a little bit more about this in a second. Then what we actually are interested in is given an element in A, which we would call a random variable, and then a certain element in this multilinear function series, I call it RA. So it's a map and it's sort of specific about A. We define another element in mult B that is supposed to satisfy this identity here. So it's sort of implicitly defined as this equation tells us how to sort of define S so that this is satisfied. And it turns out that this particular series here has the property that if we look at the product of two elements in A, so AB, that it has this very sort of interesting factorization property, which is not at all, I would say, obvious. And somehow this talk is about not about proving this identity. This has been proven in several places. I think the first place is here, Ken Dykema, in an advances paper in 2007. So it's sort of a well-known identity, this twisted factorization property for the S transform. But we will try to understand this is what's going on the right-hand side. Somehow there's a lot of structure kind of coming together in this description, and we will try to sort of put one perspective on this, which is the one of postgroups and post-Lie algebras. And so let me start with the first remark. Somehow, if this product here, the dot product, which is the product, in fact, in B, is commutative, then this whole identity sort of collapses to this very simple factorization property. This would be the factorization property of the S transform in a scalar valued context. So this was, I think, essentially, this goes back to Voiculescu. So it's a long story in free probability. And as I already said, the aim or the way we would like to approach this trying to understand what's going on the right-hand side of this identity is by looking at it as an algebraic problem, which means we would like to understand this S here, in fact, as a map that goes from this space, or this, at the moment I have not really defined what it is, mult B into mult B. And we would like to somehow understand this factorization property as a morphism property. So there's a certain product here. I've not said what it is. There's another product here that sort of absorbs all the complexity that we had on the right-hand side of the identity of the twisted factorization property of the S transform, which you can see here. So this very sort of innocent-looking product here is defined in terms of what really characterizes this identity here. Then we have to say something about this, what's called box convolution product here. And you see, and in fact, as I said, the whole point is in fact to understand this, or to describe this as a group theoretical problem. This means to see inside this huge object a much smaller set, which I call G_inf B, and to see this map S here as a group morphism, which means there's a set of elements and there are several group structures. That's what we were going to identify. And this S transform has certain properties here. And okay, so as I said before, in fact, we go even further. It's not just a group theoretical problem, but what's called a post-group theoretical problem. I will say a little bit about post-groups. They recently appeared as a sort of formalization of an influential paper in algebraic combinatorics by Gain and Audin, and there were people Bai, Gu, and others that formalized what is sitting inside this paper and named it post-groups. And in fact, we will see that the structure that we see in this factorization or twisted factorization property of the S transform, in fact, can be described as an intertwining of three postgroups that sort of are naturally connected. And this is what I will try to make more precise. And as I already said, this is sort of independent of the probabilistic perspective. That, of course, is what makes it interesting, and maybe it sort of gives more substance to it. But here at this point, I will just try to understand this factorization property sort of understood, or kind of maybe illuminated a little bit from this post-group theoretical perspective. Now, let me start with sort of, again, something that sounds very probabilistic, but somehow it's just a relation between formal power series. So in fact, here I put myself into, maybe one could call the scalar valued side of free probability, right? And so I start again with a non-commutative probability space, but this time this map phi here is a linear map that sends elements from this not necessarily commutative, but associative algebra, unital, into the base field, let's say the complex numbers. Let's take an element here, and then we look at what I would then call the moment series. Okay, so assuming that everything is such that these moments exist, etc. So this is not the point of the talk. So it's this series here. It's a formal power series in this variable z. And here we have the nth moments of the random variable a. And related to this, I have another formal power series that I call R, which then will be called the R transform. And the coefficients here are what one would call the nth order cumulants associated with the random variable a. And in free probability, it turns out that moments and free cumulants are related by this fixed point type equation, right? We see the moments on both sides. Here with this little shift, there's this the 1 plus, and maybe here I should have written, maybe I should have written here again 1 plus. And we see here somehow that that relation between the cumulants and the moments is kind of specified through this identity here. And here I assume the composition in formal power series. And when you unfold this identity here, so to say, comparing order by order on the left and right hand side, you find the following moment cumulant relation, which usually is expressed using non-crossing partitions. Right, we're on the right hand side here. We have a polynomial in the cumulants. And then so here I refer for details, or if you want, for the standard reference, is the book by Nika Speicher. And now, of course, somehow in free probability, there is this notion of freeness, which replaces the notion of independence from classical probability. And here I will not try to explain freeness, which is sort of a bit more complicated, but I will simply characterize it. In fact, it's equivalent by saying that the R transform linearizes, which means if I have two elements in my algebra A, call them A and B, and I take their sum, then this, what I call R transform, linearizes, right? So the R transform of the sum of these two elements is the sum of the R transforms. So this is equivalent to the freeness of A and B. It's equivalent to the fact that mixed cumulants vanish. And now let's try to make this jump to the R transform. In fact, one can also maybe motivate it by the fact that even though when I compare the R transform with the moment series, it looks very complicated, but it turns out that from this identity, one can also show that if you look at the compositional inverses, I write this now like this, then in fact, for the moments and the cumulants, the difference is rather small. And it's this what I would like to call, this element here, which is described through this identity, I would like to call the S transform. Right? This is now what this identity, in fact, here is coding. I have to assume that the first moment or the first cumulant are invertible. Here I assume they're just normalized to 1. And then I have this identity here, from which then I can show that the S transform factorizes, which means here I consider the sum of two random variables, and I have the linearization of the R transform. If I take the product of the two elements, after all, they come from an algebra, I can also multiply them. Then the S transform has the property that it factorizes. Of course, here, this is now the factorization without twisting, so to say. This is in a sort of commutative context, right? And here is the product formal power series, which is the Cauchy product I just recall here. And now, try to, so one way to think a little bit about this is that is to think at the level of cumulants or at the level of the generating series of cumulants. If you think at the level of cumulants, or free cumulants, usually then whenever I say cumulants, I mean free cumulants. So I assume, again, that A and B are free. So I have the property that mixed cumulants vanish. Then, in fact, I can show that if I look at the cumulants with the entries being themselves products, there's already a certain factorization going on, right? This always means this is the nth cumulant where I have the entries A, B, n times. And this, in fact, I can show that this factorizes, right? In the following sense, where I simply use that mixed cumulants vanish. And here I see that this factorization now is expressed in terms as a sum over non-crossing partitions. And the very particular crossing partition I can associate with any non-crossing partition, which is the Creveras complement, which is not essential for this talk. I'm just saying that, so to say, there's a, if you want, a local perspective at the level of the cumulants, and there's the perspective at the level of the R transform, the power series that I associate with the cumulants. And in fact, here I can express this by defining a product, the so-called boxed convolution, at the level of formal power series, which I have expressed here. And from that perspective, I can think of, this is sort of what you find in the book by Nika in Speicher in the scalar valued setting. In this sense, I can think of the S transform, in fact, as a transformation, as a map from the group of invertible power series equipped now with this boxed convolution into the formal power series that are invertible with respect to the Cauchy product. And this is what I have defined here. And then you can understand, in fact, this factorization property of the S transform really is this morphism property, right? So this is the factorization of the S transform in this sort of, if you want, scalar valued or commutative setting. And our work sort of generalizes this, or kind of looks at this factorization property. So from this point of view of group isomorphism, now in this operator valued setting. So in a setting in which somehow the product here between these objects is a non-commutative one. And so one has to be slightly more careful. And in some sense, what you see here is a lot of structure that has disappeared due to the commutativity. And in fact, that's another aspect that is interesting to see, that this sort of, it's called a classical factorization of the S matrix, of the S transform. As simple as it is, sort of hides a lot of structure that becomes visible in a non-commutative setting. And so for this, let me at least try to motivate or indicate what this operator valued setting is supposed to mean. So what is changing to this earlier setting of what I call the non-commutative probability space. So here now, I want to consider what's called operator valued non-commutative probability space, which is usually a unital, not necessarily commutative, but associative algebra. And at this point, I make it simple. I assume that B is a subalgebra and that my map E, in fact, it goes here. I wanted to say it goes, supposed to go from B into B. And the map has the properties that it sort of leaves elements in B, so to say, unchanged. And it has the property that if it looks at this product here, then I can pull out to the left and to the right the B1 and B2. So the elements of capital B play the role of scalars, so to say. And then I would like to look at nth moment expressed in terms of the cumulants, now operator valued cumulants. Again, this is sort of described by summing over non-crossing partitions. And then I see that if I, for instance, look at order 3, that if I expand this, here I make this expansion explicit, where you see here the non-crossing partitions of order 3. Okay, usually non-crossing partitions start at order 4 to be interesting, but let's simply look at what's happening here. At least at order 3, one already sees that why non-crossing partitions are useful here, because so I have this expansion. This is really just expanding this sum at order 3. I get these cumulants here, and again, of course, a single element A means that according to the degree of the size of this partition, I have that many elements A. So this is A, 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 for instance here. And then I have this factorization property for the cumulants according to this non-crossing partition. And the interesting part, of course, is here. Correspondingly to the non-crossing partition, it has really this nested structure, right? This is at order 3 visible. And here I see that I get this cumulant here that is sitting, so to say, sandwiched between the element A. And therefore, I cannot pull it out. This is really sort of it's not a scalar valued element. So here really I see the nested structure. This is this operator valuedness that sort of complicates things. And for this now, to describe in a more precise way, Dijkema used or introduced or suggested to use so-called multilinear functions or series, so formal series of so-called multilinear functions. And this is sort of the framework to study R and S transforms in the operator valued setting, right? So-called formal multilinear function series, or mult-B. Okay, and so here I mean simply n linear functions from B into B. And then here, for instance, I have what I would then call the moment series. This is the moment series with respect to a random variable A. And somehow such a moment, the nth moment, so the nth entry in this sequence of maps looks as follows. I have my elements B1 to Bn, they're arbitrary. For any elements out of B, I have then that this is the expectation, I call it the expectation value, where I sandwich the B's between the A's. So here I have my n A's, and I have in between the n A's, I have my B1 to Bn. Okay. And this is what I would call the nth moment. So in some sense, it's a map now where I have, it's a map from n copies of B into B. And now what I can do with these objects, these multilinear functions, I can compose them. This is what I've tried to, what I've displayed here. And I want to assume that now, this should be H0 here. And so I can compose two such multilinear functions, or series of multilinear functions in the way I've described here. So this is the nth entry. And this you can see on the right-hand side. I take F with K slots, so to say, and I fill these K slots with elements from H, such that in total here I have my n elements B1 to Bn being sort of composed into this composition of the two functions. And then I can also multiply two such series because I have the algebra structure on B. So this is the multiplication of elements from mul B. This is essentially, say, a non-commutative Cauchy type product, as you can see it here. And usually one has to be slightly careful here, and somehow one puts the circle before the dot. That's what I've tried to indicate here, right? And then something that Dijkema showed in this paper from 2007 is there's this right distributivity of the composition over the product. This will be crucial in the following. So which means if I take first the product of two such elements from mult B, and then I compose K into it, then this is the same as taking the product of, I think I made something wrong. This is probably supposed to be F composed K and H composed K. Sorry for that. And this distributivity will be important. And okay, so now, as I said, at this point, we have been essentially algebraic. We've now an object with two compositions, multiplication and composition in the sense of composition. And now we would like to sort of focus on a specific set of elements here. And this is what I call G-inf. And here I assume that the constant part in my multilinear function series is just 1. Okay, and I take G-diff, and here I assume that the constant term is 0, and that so to say, the coefficient or the first entry in this, or the second entry then, is just the identity map. So something in a sense inverted. And the inverses here, with respect, I can invert these elements in here, and the inverses here I call F inverse and F circle inverse. So this is the multiplicative and compositional inverses. And now the crucial part here is the following, that in the scalar part is a little bit under the rug, and here it becomes critical that I can move elements from G-inf into GB by multiplying with the identity element, right? Maybe I should have emphasized this composition. The identity is written as capital I, and for multiplication, it's just the usual element in A, but now it's as element in mult B. And now I can take elements in Ginf, and I can multiply them from the left or from the right. And as a result of this, since these elements here start with 1, I'm ending up then in GDiff, right? And here I formulate this in terms of 2 maps, lambda and rho, where lambda means left multiplication with the identity, and rho means right multiplication with the identity. Okay, and this will be now sort of the central point of this presentation. From here, now a lot of structure actually can be deduced. And as I said, so in fact, it turns out that now these particular elements, so those that are always multiplied with the identity from the left or from the right, now as a subset in GDiff, they actually themselves form groups with respect to composition. So they're closed under composition, right? Let's simply check this. So we take 2 such elements. So they have the form IF and IG. And then I compose them. And then I see by the right distributivity of composition that I get the following expression here, right? And here I see, of course, that again, it's something of the form I times and then something else. And this something else, of course, is what's really interesting, but this will come in a second. So taking 2 elements of that form, we obtain again an element of that form. And if I think about the inverse, so it is, after all, IF is an element in GDiff. So the inverse sort of has to satisfy the fact that if I compose F with its inverse, I get the identity. Now I can simply explicitly write down what this composition is. And from here, I can deduce a way to compute the inverse. Now, in terms of capital F, right? At the end of the day, I start with capital F, I multiply this with the identity, I end up with something in GDiff. And I would like to understand, in fact, the inverse with respect to composition in terms of this element in Ginf. This will be the main point of the what's called the S transform. And now let's get to this. So I define now what I call left and right S transform. So everything here sort of can be either looked at it from the left or from the right. Like we have these maps lambda and rho, and that's what I'm trying to explain now. So I define now what I call the left and right S transforms. Right? These are 2 maps. These are 2 maps from Ginf into Ginf. Okay, they're not from Ginf into GDiff or anything like this. They're really operating on Ginf, on those maps that are invertible with respect to the usual multiplication. And they're defined like this, so that the left S transform and the right S transform, they take an element, then if I multiply it by the identity, so if I push it into GDiff, this is the inverse in GDiff of the element IF, right? And the same from the right, that it's Fi, right? And from the computation that I just showed to obtain the inverse, you can in fact find these 2 equations here that allow you to compute inductively the left and the right S transforms. This is just another statement of what we just saw here. And an interesting thing is you can also show the following, and you will see, you remember maybe from this twisted factorization that this sort of sandwich operation or adjoint operation, if you want, will be crucial. And this you can express in the following way. Now, let me again try to connect to, so to say, the way one should think about this from the point of view of moments and cumulants. I'm now becoming a little bit more general. I consider a B-valued probability space. So we have an algebra A, and then we have another, not necessarily subalgebra of A, but the B algebra A, which means that A is a B module over B. And we have a unital linear map, our expectation, and it has this property. We already have seen this. We have the moment series. And then I define now what I call the free cumulants. The free cumulants as an element in Ginf, which is characterized by this identity. Okay, so I start with the moment series. They are given to me. Then I define the free cumulant series as an element in G_inf by this identity. And then somehow we have an element in here characterized by this identity. I define its S transform, right? Which is what I've expressed here. And now the left-hand side, so to say, kind of captures the idea that this is this map, the left S transform that maps this the cumulant, the free cumulant series into another element in G_inf. And now let's try to, I made a remark at the beginning that was about that I can look at this factorization property either, so to say, at the level of cumulants or at the level of the generating series. The analog statement here, in fact, is captured by this identity here, that is, which also can be expressed as a certain box convolution. But where the right-hand side here now is far more complicated, and you see it doesn't contain anymore this non-crossing partitions and their Krivas complement. Instead, what we did, this is the reference to the earlier work with Timothée, is we tried to prove this using planar binary rooted trees, which somehow has a certain advantage because it allows to kind of capture the non-crossing partitions and the Krivas complement in a single object, a planar rooted, binary rooted tree. And then within this setting, right, here again we have the linearization of the cumulant series, which is equivalent to the freeness of A and B. In this setting, we proved this formula, right? Which means we simply showed that this S transform, which I defined here, in fact, satisfies this twisted factorization property. So I'm saying this because I will not try to prove this identity. I will try to sort of unfold a certain theoretical perspective on this identity. That's why I've mentioned this briefly here. So again, our point here is that this is given, this has been shown, this S transform satisfies this factorization property. Now we would like to see whether this fits some nice group theoretic scheme. And this we do now by essentially trying to understand this intertwining here of multiplication, composition, and the inverse with respect to multiplication. The particular fact that the identity appears here, we try to sort of put this into this framework of postgroups. This will come out in a few slides. Now, as I said, so the twisted multiplicativity of the S transform, as I said, combines elements in mult B as well as the products we have there, so the multiplication and composition. In some sense, I would say it's not obvious that a non-commutative generalization of this factorization of the classical S transform, so to say classical in the sense of commutative, would satisfy this identity, right? In hindsight, it becomes clear. So the whole thing here, if it was commutative, would collapse to what we know as the usual factorization of the S transform. But it's not so clear how to generalize this to the non-commutative case. And let's simply look at this in a more systematic way. And this means by somehow identifying the operations here and the way that they are put together from the point of view of postgroups. There's something on the screen. Okay. So for this, I introduce now operations, products, and then I will show that they have certain properties that sum up to in fact, three postgroup structures which are tightly connected. And that's the interesting observation here. So I take, again, two elements, and then I define a left star product and the right star product, which simply says you take G and you multiply it from the left, multiplication in the sense of the usual multiplication of those elements in mult B. But in F, now you multiply it with F, but on F you operate, so to say, by composition with IG, which makes sense because G_inf is pushed by multiplication with the identity into G_diff, so it makes sense to do composition. And the same I can do from the right. Now, what you can show is that on G_inf, these two operations define group laws, right? Which is maybe not so obvious, and they have the same unit. And we can do another thing, since we thought here about doing things from the left and doing things from the right. We can also do it from the left and from the right at the same time. And this is what this is, the square dot product, where again, we take G, then multiply it from the left with F, but we compose into F G inverse multiplied with the identity multiplied with G. Again, this makes sense. I can multiply these are elements in G_inf, and by the multiplication with the identity, this whole thing here lives in G_diff, so it makes sense to do composition. And once I have this defined, this square dot, I can re-express the twisted multiplicativity of the S transform in terms of this expression here, which is sort of putting a lot of complications into the simple symbol here that for the moment I call a square dot. But it turns out that G_inf with this square dot in fact again forms a group with the unit 1, right? And the inverse, so associativity is right here, bit tedious, so I don't want to do this. But one can show that the inverse with respect to the square dot looks as follows. It's the multiplicative inverse of F composed with the multiplicative inverse of F times I times F. Everything here is the usual multiplication. And then I take the inverse with respect to composition. And this is what I compose into F inverse. So complicated maybe, but in fact, it shows that this square dot here defines another group structure on G_inf, right? Showed in fact that when you multiply this with F, then you just get 1. So we have 3 products. And now let's introduce the object that will identify each product, and then also the 3 products together. And this is the notion of postgroups, which was introduced by Bai and co-authors in 23. And so let me recall what this is. So a postgroup consists of a group with respect here to the dot product, and a map, or the postgroup action, that takes 2 elements in G, maps it into G in the following way. So it multiplies, so to say, or acts from the left with the element B on the A as automorphisms, right? And in a particular way, in such a way that if you act first with B on an element C, and then you act with B, then in fact this is the same as multiplying A and B, but multiplying with a new product, the so-called Grossman-Larsen product, which is defined here, right? And somehow again, we see here something that we have already seen before, somehow multiplying from the left, dot, and a certain action. Okay, so which means I can move the brackets here in this, I can move successively from the left, but I can move the brackets to the left. Then I have to, then I get here a new product. And in fact, what one can show is that this so-called Grossman-Larsen product, in fact, defines a new group law on G, right? Which is the Grossman-Larsen product or the Grossman-Larsen group. This is what I call a post group. And as a remark, if the group G was commutative, then this notion here, this notion of post group, in fact, would reduce to pre-group. And post and pre here sort of comes from the fact that these are the group objects corresponding to what's called a post-Lie algebra or pre-Lie algebra. I will get to this a little bit later. So now, we see we have a group, we have an action of the group on itself. In fact, we see that the set G equipped with a new group law defines then a group that is acting on the original group G dot. Right? This is what, in fact, is what we are talking here about. And now let's try to identify post groups on G_inf. Right? So I take two elements and I define now the left and the right action by simply composing G with either F multiplied from the left with the identity or F multiplied from the right with the identity. And again, for F and G, composition would not make much sense. But now, since I can push F into G_diff, this composition makes sense. And I can have another operation of that sort, where I compose G now with this sandwich operation, F, or the adjoint operation of F inverse with F. Okay, then what turns out is if I take G_int with its original product, now then I can, in fact, I can identify, or I can equip this group with three post-group structures. And I've noted them here. So this is with respect to this left action, with respect to the right action, and then the star L and star R modulo a twist, flip in the order, are the Grossman-Larsen products, right? Remember, these were the products we started out with at the beginning. And also, with respect to the triangle operation, where we do, so to say, from the left and from the right, also forms a post group, now with the Grossman-Larsen product being the square dot and a little flip in the order. That's important. Okay, so now we see here that we get three post groups, starting from the fact that we can either operate from the left or from the right with the identity, right? And now, in fact, you can show that these actions actually are group automorphisms, so it makes sense. And here I try, and of course I would have to verify also that I have this property of the post group that allows me to express the iteration of the here left action, say, for instance, in this form here, where I can now identify the star L product. Okay, and okay, this is, so to say, a very sketch of the proof that in fact we have post groups here. And now the interesting part here is when we sort of close the circle and get to S transforms is that, remember, the S transform is essentially about sort of expressing the inverse in G_diff by a map in G_inf. And this is what we're doing here. So sigma is the inverse map with respect to the original product in G_inf. Then the left S transform is the inverse map with respect to the star L operation. Then I have the right S transform. This is with respect to the star R operation. And I have the square dot S transform expressed here. These are these inverses with respect to the square dot. And you can show that all of those are involutive, right? So which means if you apply this twice, you just get the identity. And it's also interesting to think about always how to connect back to the fact that if B was a commutative algebra, that all these structures essentially collapse because there's no distinction between left and right. And we get a single Grossman-Larsen product. And in fact, what we find is a single pre-group with a single pre-Lie action, so to say. This is just a remark. And now, these Grossman-Larsen products, and therefore the post-group structures, are related, they are connected. And by this I mean that if I take two elements in G_inf, then I can express, for instance, this triangle operation as a combination of the left action, the right action, and the left S transform. And with this at hand, I can express the square dot in terms of the left star operation and the right triangle operation, right? I've tried to show this briefly here and here. But it's simply, the message here is, without doing these computations, they are not complicated, but they're somewhat difficult to parse. There's a lot of brackets here, so I will not try to really do this. But the main message here is that we see here that these three operations, these actions, triangle, triangle left, triangle R, are related, right? And the same for the square dot product and the left star. One can also do this with the right star and then the right S transform. And one more operation is needed to express this twisted factorization of the S transform, is that so when we have this Grossman-Larsen product square dot, then I can express the then I can, again, I'm just expressing here the twisted multiplicativity of the S transform. Here I have the cumulant series with respect to the product AB. I compute the S transform, or in this case, then to be more precise, left S transform. And I can express the twisted multiplicativity simply by saying, okay, this amounts to the product of the left S transform of the cumulant series of A with the left S transform of the cumulant series with respect to B. And now, of course, I can invert S, it's involutive, so I can define a new product. I can transport this square dot product by the left S transform, and I define this box convolution product. And in fact, turns out the fact that I've chosen here to work with the left S transform to define the square dot is not essential. I can also do this with the right S transform. And in fact, the left or the right S transform becomes a group morphism, isomorphism between G_int with the square dot and G_int with this new product, the box convolution, right? And the inverse here is relatively simple. So we have another sort of S transform with respect to this new group structure. And now you can express this box convolution again as a combination of all those structures that we have seen before. So here it's the left star product, the right triangle action, the left S transform, or everything sort of flipped now with the right star transform, the right star product, and the left action and the right S transform. So it's maybe not obvious what I'm saying here. It looks maybe convoluted, but the point is simply that all these structures, these group structures, are related, right? And again, to make sort of a sanity check, if B is commutative, or if B was commutative, then we have that this left and right product identify, the left and right, the right and left action identify, and the box convolution product is commutative, as it should be from when comparing with the work of Nika and Speicher. And in fact, moreover, all these S transforms, now I'm not talking about the commutative case here, just in general, these S transforms, we have several of them, they are related. So I can express one in terms of the other. That's the also interesting part that simplifies a lot proofs, but it also shows that, again, these groups that we are observing here are very tightly connected, which is expressed by in terms of their inverse maps. And let me take maybe to make the connection somehow to the algebra side, and maybe then also justify the non-associative algebra part here. Now, if I look at the Lie algebra corresponding to G_inf, which means elements in mode B that have no constant term, then I can linearize composition. And if I linearize composition, then this linearization, I express this here by these curly brackets, in fact satisfies the following identity, which identifies it as a right pre-Lie algebra. Right? So the linearization of composition for those elements here leads to a pre-Lie algebra, to a right pre-Lie algebra, which means left Lie admissible algebra of that form. And now the composition, the distribution of composition over the product at this infinitesimal level, at the Lie algebra level, is expressed as follows. So this is essentially the pre-Lie product of H into the product of F and G as elements in the Lie algebra. And this has the following, if you want, Leibniz type property. And this is an interesting observation that came out of our work, is that for this pre-Lie product, the left multiplication with the identity satisfies this operator identity. So we get a pre-Lie Nienhuis map. And this has interesting implications that I cannot explain here. It's not enough time for that, but it's sort of somewhat unexpected to find here a Nienhuis map. Personally, I would have expected a Rota-Baxter map, but it's not like this. Now, let me introduce one more object. This is the so-called post-Lie algebra, which is a Lie algebra with a triangle operation that has no further properties and the following two identities. So if the triangle operates from the left on the Lie bracket, it has this Leibniz rule. And if the Lie bracket triangle acts on Z, then I have this difference of associators. And this is what defines a post-Lie algebra. And what you can show is in a post-Lie algebra is that if you take the sum of the original Lie bracket and you anti-symmetrize the triangle operation, then you get a new Lie bracket, right? And if this Lie bracket here was 0, then the post-Lie algebra, in fact, would reduce to a pre-Lie algebra. And now what you can show is, and this is somehow getting to the end, is we had this pre-Lie operation here. Now, if I twist it, so to say, by multiplying either from the left with the identity or from the right with the identity, and I put here an extra minus sign, and also take it outside, then these two operations here, black triangle left and black triangle R, in fact, define the post-Lie products with respect to the original Lie bracket on the Lie algebra Gnf, right? And if I take the sum of the two, this is what I've expressed here, I get a third pre-Lie algebra, post-Lie algebra, or post-Lie operation, right? And in general, you can show that if you have two post-Lie algebras and you have that the two post-Lie operations, post-Lie actions satisfy this mixed pre-Lie type identity, if you want, then the sum of the two post-Lie operations is another post-Lie operation. And you can transfer this, you can integrate these post-Lie algebras, or the other way around, I deduce these post-Lie algebras from the post groups that I identified in the context of the S transform in mult B. You can translate this identity here, this observation that two post-Lie algebras add up to give a third post-Lie algebra. You can also identify this as or you can transfer this or integrate this observation at the level of Lie algebra to a statement at the level of post groups. And in fact, this is the general statement that is behind this sort of proliferation of post-Lie algebras in the context of the S transform. We have 3 of them. They sort of are intertwined in this twisted factorization or property of the S transform. And I think that's what I wanted to say. Thank you.
Thank you very much. Are there any questions? So if not, I wanted to ask something.
Yes.
Is there any meaningful hope for a classification problem?
I have not worked on this, but I think Dietrich Burde has worked a lot on saying more about, I think, finite dimensional post-Lie algebras and also I think pre-Lie algebras, and to sort of look at them in a more, say, systematic way. I've not worked on this. For me, it's more like trying to understand this, say, properties of the S transform in free probability from that point of view.
And does the theory interact with the classical algebras?
Maybe I'm not really an expert on this. I don't. I suppose so, but I don't know.
Okay, so thank you very much. Let's thank Kurusch for a very interesting lecture. And the schedule says we have a few minutes, so let's just start on time in 1 o'clock, the original schedule. I guess we probably have like 10 different time schedules, each one of us, but let's start on time.
Thank you.